involved integral. And so just as a reminder, the theorem that we worked out for Poisson's equation, okay, was essentially that the form of Poisson's equation on the unbounded domain has, as long as f is compactly supported, NC2, the following solution, which is essentially our convolution of phi with f. And we can write this as the integral over Rn phi of x minus y f of y dy. Okay, and we needed continuity, twice differentiability actually of f in order to apply a change of variables. Improving this, we also needed the compact support because the integral over the fundamental solution isn't necessarily bounded. And then, yeah, like I said, we needed to remove that singularity there at the point x equals y in the fundamental solution. So let's start today. In general, what we want to cover today is what's called the mean value property and the max principle. Okay, and these are going to be useful for several things, proving uniqueness results, for instance. Okay, let's start with a quick warm-up problem. Okay, maybe take 5 to 10 minutes to work on this, and then we can go through it. So if you look back in your notes, we wrote down Green's first identity on Wednesday. And I just want you to use Green's first identity to prove that if the Laplacian of u is equal to 0 for x is in some domain, call it omega, and u of y is equal to g of y for y in the boundary of omega. Okay, the solution to this boundary value problem is unique. Okay, and in particular, I will go ahead and just give you Green's first identity, right? Green's first identity, right? You can look back in your notes. But essentially, we have that the integral of v times Laplacian of u is equal to the integral over the boundary. This is sort of like high dimensional integration by parts. And the normal derivative of u with respect to n, integral over minus the integral over the gradient of v and the gradient of u dx, right? So you've used this before, okay? And so see if you can take the next step of figuring out, remember what we typically do for a uniqueness proof. What is a function that we usually define when we do a uniqueness proof? And also keep this in mind that we have Green's identity here to work with. I'm telling you the mechanism to use. And see if you can put those things together in order to prove uniqueness. Essentially, if you have two solutions, U1 and U2, that they have to be the same, that they have to be equal. Okay. Right. Any progress? Thumb up. All right. Anybody want to share what worked for them? Where they're working on?
I can share.
Sure.
So I started by looking at the integral of the square of the magnitude of the gradient of u, because that
Yeah.
kind of matched the form of the integral on the right.
Okay. Like
Um,
that.
yeah, because you can rewrite that as grad u dot grad u.
Okay.
Um, and then you solve Green's identity for that last term there. So set it equal to the difference of the other two terms.
All right. Yeah. So you're saying you get this. Okay.
And then in that second integral on the right, the Laplacian is 0. So that integral is 0.
Vanishes. Okay.
And we're trying to solve the condition where the boundary condition is 0, because that's what happens when you subtract two solutions.
I see. So you're assuming here that u equals u1 minus u2.
Yeah, sorry, I guess I could have started there.
Yeah, that's cool.
And since the integral on the left is over the boundary, we know that u is 0 in that integral, so that integral is 0 too.
U is equivalently 0 on the boundary. On x is in this, right? Okay. So then, yeah, this thing becomes, yeah. So then you're saying this goes to 0. So
Yep.
then everything equals 0. Okay.
So then the gradient is 0, so u is a constant, and to match the boundary conditions, it has to be the constant function 0.
Oh yeah. So then since u1 minus u2 equals 0 on this, right? So u1 is equal to just u2. Squeeze that in there. Right. Okay. Yeah, that's essentially what I had. So good. Questions about this? All right. Thanks for taking us through that, Sage. Okay. So yeah. So essentially, another uniqueness proof. Essentially, we follow the same program, or not the same program, but a similar program to what we had before, which is essentially just take the difference and show that some integral involving the difference is equal to 0. But that should be maybe a bit reminiscent of energy methods. Maybe you could think of this essentially as an energy of the problem, right? And we're showing that that energy is 0. Therefore, we can show that the difference is 0 there. Okay. So that's one way of proving uniqueness. Note that we were assuming, right, continuous differentiability of u in order for this thing being 0 to imply that this equals 0, right? So just remember to think about that as you work through these things. What assumptions are you having to make on regularity? Okay.